So hello everyone. Welcome to the CeADAR online tech talk series. So I just present a bit the format of the talk. We are going to have the talk, the presentation for 40 to 45 minutes. And then after that, we stop the presentation and then you can ask questions. For today, we have Dr. Ihsan Ullah, who is research fellow of CeADAR, and Ihsan will give a talk on federated learning framework tools and example. So I hand it over to you, Ihsan.
Thank you. Thank you, Kwan, for giving me the chance. Yes, I am Dr. Ihsan, as Kwan highlighted, and I will be presenting an overview of the federated learning. The outline of my presentation is that first I will start with deep learning and its challenges and why we need federated learning. Then I will introduce federated learning, its components, and how it is evaluated. It will be followed by a few real-world examples in different sectors and challenges that researchers are facing. In the end, I will conclude it with the presentation with some takeaways. Deep learning is a branch of machine learning that is taking machine learning closer to its original goal of providing artificial intelligence. The term deep learning was coined after the re-emergence of neural networks with AlexNet model. These three are the authors who proposed the paper and the model. And they coined the word deep learning that I will say disrupt the research community of how we approach the problems rather than the traditional approaches. Now everybody, the first thought is to whether can we use deep learning for it. It was similar to a previous model, a convolutional neural network like proposed by Jan Lee-Kahn, but these three increased number of layers and kernels, introduced ReLU activation function, implemented in a way to run it in parallel on 2 GPUs for the first time. This make it able to be trained on large-scale object recognition data set that contain 1.5 million images. And since then, various deep models like DenseNet, fully connected networks, ResNet, GoogleNet have been proposed that are showing promising results in various fields and applications. For example, autonomous vehicles, health, robotics, object recognition, retail, and other areas. And you can see that just from the citation that within the past few years, it was proposed, released in 2012. And since then, it has more than 72,000 citations. So it's like 99,000 plus citation per year. So just imagine, this is like pretty good, and how it disrupts the research community. Deep learning has been used in almost all industries and sectors. For example, in health, for diagnostic medical image processing, drug generation based on an estimate. The global forecast market for healthcare analytics by 2024 is about $50.5 billion US. And similarly, it is being pretty big for other manufacturing, finance, and retail sectors. Once we used to worry about lack of data, but now we have tens of thousands of data available. We were unable to store the large amount of data, but now we can easily and freely or at low cost can store it. However, it needs to be GDPR compliant or need to be kept secure. Otherwise, it became a problem for the companies or organizations. In the past, softwares were expensive, algorithms were hard to train. Now it's open source or easy to train and even freely available. Similarly, previously computer processing was slow. Now GPUs exist that support fast processing and made it possible to process such large amount of data in hours or days that was not possible to process in even months for generating valuable information. we are getting good, but still deep learning has challenges. Like deep learning networks are called data hungry because they have millions of parameters which need a large amount of training samples. However, getting data or getting labeled data is a main challenge that is still exists. Similarly, anonymizing the data to be GDPR compliant and to keep it secure for transforming such large amount of data over the internet continuously is another issue, as it is costly. Let us consider that if a retail store which have an existing camera system in their or surveillance system in their store, and they wanted to upgrade it to have customer analysis. So it is always considered better that you utilize the existing platform rather than giving them a new devices. So for that, if the existing system is very good in, for example, the video cameras provide good resolution videos. So in real time, if you have to transfer them to the cloud to process is costly because it will need more bandwidth. Similarly, its security and the performance of the models are issues. So the solution is federated learning. According to Wikipedia, federated learning is a machine learning technique that trains an algorithm across multiple decentralized edge devices or servers holding local data samples without exchanging them. Or in simple words, a technique that sends a model to train on data at various remote devices, nodes, or servers without bringing the data from them to the main server in order to preserve the privacy of the organization or the data they have, and to keep them secure the data, so not to lose that, and to have a better generalized models from various data sources. So the traditional approach, here you can see the traditional approach of learning a model. You have some data, you train a model within that, for example, organization A or firm, and the research data scientist train the model. Once that is trained, you deploy it, or if somebody else needed it, you send it to the other store as well to deploy. But if the organization B data is slightly different and they agree with you, they will send you their data to you that you can utilize to enhance your model and send the enhanced model to organization B to be deployed. But this, most of the time, a question arises, does it violate GDPR and other privacy and security rules? Or is it GDPR compliant? Hence, many companies or organizations are not happy or able to share data. And that is a blockage for research data scientists or a data engineer, how to enhance their model if the data is not available or not available in right amount or not properly labeled. So Google introduces federated learning. Federated learning is about transferring a trained model from server, as we previously mentioned, from server to a remote organization to fine-tune it over the local data of that organization. Once the network is fine-tuned, it is resent to the server to update the baseline model on the server, which is further forwarded to other organization or clients after aggregation. This cycle continues and the model is regularly kept updated on the data from each organization without leaving the premises or compromising the privacy or security of the data in that organization. Now, the point is there can be various strategies for the flow of the model and when to update. Should it be sequentially or be updated or aggregated and then sent to the next one, or send a complete scratch model to all at once and collect and then aggregate and then update it? I left the lines on the diagram just to show some of the complexity over here. That it's not just simple, but the aggregation is one of the most research topic in this, or subtopic in this federated learning. While inference on edge computing model is straightforward, the distribution of the learning task is seen as increasingly important in these contexts. Federated learning provides learning infrastructure that aims to maximize the privacy of original data sources while providing a degree of scalability and cost sharing potential. So federated learning, as we have seen in the previous slide, that it has two main components, that is the server and the client node. Now, to discuss them briefly, the central and the client, server and the client has mandatory and optional components. The mandatory are the components that perform the main federated learning operation, whereas the optional component assist or enhance the federated learning operation. The central server initiate and orchestrate the training process, whereas the client device perform the actual model training. In central server, the mandatory components or subcomponents are the aggregation of the model and then evaluation of the model, whereas others are optional areas, for example, doing advanced aggregation, or for example, going one step further to further secure it and doing secure aggregation, in which they change or the approach is to change the data or through a proper way, and then they combine the data so that it is more secure. Training management, incentive management, communication, coordination, and accountability. Accountability in the sense that how or which of the model, when the model will be accepted and when it will be rejected from a node. Because the main challenge is that in federated learning, in traditional learning, you can have a fixed size of data, but in federated learning, each node can give you varying amount of data. So are you going to accept the model trained on varying size of data or not? For example, if we have less amount of data and the model is trained for the same number of epochs, it might overfit on it. So is it good to aggregate or average an overfitted model with the other models? I don't think so. So there are accountability points. Similarly, in client devices, the mandatory processes are the data acquisition, processing, training, and inference, whereas the data augmentation, provenance, auditing, feature selection, and fusion, model compression, advanced privacy and security are the optional processes. In the next slide, I will just briefly discuss one of them, that is the model aggregation. There are multiple approaches of aggregating the models. For example, the baseline approach is to send the calculated gradients over a set of samples. I mean, once a batch of is processed and the gradients are calculated, send those to the server. The model will be aggregated based on the gradients in the server, and then the updated model will be resent, and then the next batch will be processed and the process will continue. This is a time consuming, as it has to be done multiple times, for example, for multiple batches or iterations. However, it helps in the convergence. I mean, it is better than the second approach, that is to train the model locally for multiple iteration or on all the batches, update the model, and then send the updated version. And this is fast, but sometimes it is hard to converge the model in simple averaging or simple aggregation. Due to the limitation of these about two various other and some other reasons, other approaches are introduced. For example, the safer approach, which compress the models and then send so that to have secure computation, as well as need low communication and computations. So I mentioned that there are various components that are being researched, but the main most discussed phase of the federated learning that is being discussed in the literature review is the model training. Only a few studies cover data processing, feature engineering, model evaluation, and only Google has discussed the model deployment, their Gboard. They have explained that pretty well, and that clarifies many concepts and how you can take that as a role model of how to utilize it for your own problem. Model monitoring and project management are not discussed in the existing studies that I found, but more studies are needed for the development of production level federated learning systems. Now, coming to the evaluation means when we have a model, we do have to evaluate it. So it's not just the model performance here. In the case of model performance, we use the same, researchers have used the same like training loss, area under the curve, F1 score, and other matrices that are common to the traditional learning. But in this federated learning, we have communication that is being one of the major role plays. Mean you receive models from other nodes and then process on that. So communication cost is a factor that is being quantified by the communication rounds against the learning accuracy, the satisfying rate of communication, the communication overhead versus the number of clients, the theoretical analysis of communication cost of data interchange, and several other factors are being considered for it. The other one is the computational cost. I mean, how much your model or federated learning model is efficient in terms of computation cost. It is the assessment of computation, storage, and energy of resources of a system. The computation resource is quantified by the computation overhead against the number of clients. Other factors that are convergence rate and dropout ratio. These are used to evaluate system performance. The convergence rate is quantified by the accuracy versus the communication round system, running time, or training data epochs. The dropout ratio is measured by the computation overhead against the dropout ratios, and which are showcased, the results are showcased by the comparison between a communication overhead for different dropout rates and the performance comparison against the dropout rate. Incentive rate is assessed by the calculating the profit of the task publisher under different number of clients or accuracy level, the average reward based on the model performance, and the relationship between the offered reward rate and the local accuracy over the communication cost. We need some other incentive mechanism for the motivation of the people to contribute, or the for example, in the Google Gboard, everybody contribute in it, those who use Gboard, but there might be some other where we need to ask, or in majority of the cases, the company has to ask the permission from the user to provide their data. So if it is, can we provide some incentives to them so that they can volunteer in providing their data, and that can help us in improving our systems. System running time evaluation, that is its results are presented as the total execution time of the training protocol that include computation time plus communication time, the running time of different operation phases, and the running time of each round against the number of client devices. Then we have some other matrices, but those are qualitative metrics that are for data security analysis on differential privacy achievement, performance of encryption and verification, how the confidentiality is guaranteed for gradients and for the data that are shared, or the model that is being shared, and the auditability of the gradient collection and update process. Now coming to the one of the example that is Gboard. Federated learning was introduced first by Google, and one of the well-explained example of federated learning is Gboard language modeling, where I hope many of you have used this feature from Google, where your mobiles save your typings in the Gboard and then train a model locally over it, and then it send it to the Google server. By this, their model is improved day by day, and you see the next relevant words while typing, as you can see in the diagram or in the picture on the right bottom, that if you type, the next words are suggested, like let me know if you have, and the next word is suggested as have or need or have any. So this is based on your previous clicks or your previous typing. The federated learning strengthens the predictions and increase the accuracy for them by 24%. And in addition, they reported that due to this, there was an increase of 10+% clicking the suggested words rather than typing it by themselves. Similarly, they used this approach for the emoji predictor. They reported that 7% increase was reported in the accuracy, and there was 4% more clicks on the emojis predicted by their Gboard. In terms of their action prediction, for example, when you type some word and a GIF or sticker is appeared, in that case, there was 47% reduction from before. When they used to do it before federated learning, there were unnecessary or wrong suggested GIFs used to appear, but now that was being reduced by 47%. The next example is related to health, which is, we all agree that this is one of the most important, I will say, application could be. I mean, if we can further utilize federated learning for health data, that will improve our systems. We have CT scan, X-ray, MRI, and the first challenge for us is that the hospital trust, to gain the hospital trust. That was the first challenge for us. But now, with the help of federated learning, there is a possibility that we can ask them that we are not asking you to give us data. The data will be in the premises, but we will give you the model to train on. But despite that, there are challenges like each device. For example, different biopsy from different microscope will have different sizes, different slide of picture, different color. CT scan are from different brand. MRI has different sequences. MRI has different acquisition time. So a lot of these issues will arise when the data is collected, and we need to normalize that before the model is being trained on. So there are a lot of challenges even then, but the main challenge of the privacy or the GDPR is being solved with the help of federated learning. Oken, well, this is an startup that first utilized or proposed federated learning for health data, and their motto is to use federated learning to accelerate medical research. And they are also now moving towards the COVID-19. But here on the right, you can see an example from their current work that they are working with NVIDIA Clara in King's College London, in which they are showing brain tumor segmentation, where the brain tumor is segmented by a model trained using data from a single institution, as shown in red in the image. And a federated learning model shown in green that is trained over data from multiple institutions. So you can see that the red shows that it segment also non-tumor area and may result in false positive or false negative. But the green, which is from federated learning, it tightly segment the tumor area as it is being trained by varying type of data from different institutes or hospitals or research centers. And therefore, the model is more agnostic, or it has more generalization power. So another example from health is utilizing EEG brain signal data. Here you can see that an example of EEG brain signal was utilized for emotion recognition or epilepsy detection. In their simulation, they have used 3 data sets and trained their proposed model on single data set versus combination of data set over different computer. And they reported increase in performance when multiple nodes and data sets are used for training. So in other words, the federated learning enhances the performance in terms of their accuracy. The more the nodes and data, the better the performance is. The next example is for the retail. For example, as I previously mentioned in my talk, is that if there is a full chain having multiple store and they wanted to use their vision system or security camera so that they can learn from their customer in the store from various stores, and they will not collect. I mean, they wanted to collect the recording of the videos from various stores to process it so that they can recommend product or sales for their customers. But with the help of federated learning, they don't need to bring the data from or store the data. Rather, they can utilize it in the specific store and process it in the time, and may send a recommendation to the customers. Now, coming to the tools, one of the first one was the TensorFlow Federated Learning, TFF, and Core. Then other came, and as I mentioned, NVIDIA before. NVIDIA Clara is specific for health data. It's a library from NVIDIA. Similarly, Substra is from Substra Foundation, and this is initially was proposed by the Okin startup, but now the Substra Foundation has taken over that, and it is being under Substra Foundation. IBM Federated Learning Library, Federated AI Ecosystem has Fade Serving and KubeFade, which involve both Docker for composition and Kubernetes. So just to highlight that. And there are several other libraries and tools that one can utilize, but these are some of them which has pretty good helping material. Now, coming to the open challenges that still exist, one of them is that benchmarking schemes are needed to evaluate the system development under real world settings. I mean, we don't have for training a deep learning model, we have, for example, ImageNet data set. But for this, we don't have proper data set that we can use and evaluate. So evaluate the performance with rich data sets and representative workload. So we need benchmark schemes. In practice, the data generated on clients might be mislabeled or unlabeled. So we also need some possible solutions such as semi-supervised learning based techniques, or the label the client data by learning the data label from other clients. Or we federated learning still leaks systematic architecture design to guide the methodological development. System architecture can provide design or algorithm alternative for different system settings. Similarly, human-in-the-loop domain experts are expected to be involved in the federated learning process to provide professional guidance, as end users tend to trust the expert judgment more than the inference by machine learning algorithm. Or also to get some volunteers to properly label the data. Similarly, there is no proper incentive mechanism that can motivate people to provide or contribute in the system. Some others are model compression, multitask learning, one-view short learning, and federated transfer learning are some open problem challenges that are not yet explored and can be useful for federated learning. So these are some not just challenges, but also open areas that researchers can explore. But again, if we have a benchmark data set, that will be pretty good. Now, to conclude my presentation, federated learning is more appropriate on device data. I mean, when the data is more relevant on the server side, side proxy data. I mean, when the data is more private, like in the health sector, so that's federated learning is an ideal approach for that scenario. In addition, when the data is too large and there is real-time communication, I mean, and a communication requirement for transferring of their data. So in that case, rather than having continuous communication that need large bandwidth and cost to transfer, we can use federated learning on the edge device or on the node that can help us in reducing the cost. In addition, for one thing is that federated learning currently is more ideal where the labels can be inferred naturally from the user interaction. For example, as we have seen in the typing case on Gboard. So if the labels are like those, then it is easy. But still, for example, in the case of health, where the labeling has to be done by professionals, for example, for the segmentation scenario, the labeling has to be done by professional doctor, expert. So then still we need volunteerism in that scenario, and we need some incentives for them. And the last but not the least, there are several tools available for it that one can utilize. They are open source, and there is a lot of helping material for that we can use. These are some of the references from which I made this presentation. I thought I should highlight them. Thank you so much for listening.